Alright, now that we have the equations of equilibrium, we can solve for the unknown member end displacements. There's your general stiffness expression. Stiffness matrix times the unknown displacement vector plus the fixed end force effect equal the applied nodal force effect. These get taken over to the other side, so there's just a square matrix times the displacement vector equals a force vector. And that's what we've got here. 3 by 3, the 3 unknown member end displacements, and then this is the effective loading side over here. Right? And so we'll put all this into, well, I put it into a math solver that turned out to be Excel to do the matrix inversion and the matrix multiplication to get then the B, C, and D values. Of course, don't forget that those were just shorthand for the EK rotation at B, EK rotation at C, and the EK translation, which happened to be up here at the top right hand side. And we got values then of a positive value for B. Right, now take note that that means positive is clockwise for a rotation, and that's sure enough then what we had anticipated, that this top left joint, which was B, would rotate in that clockwise fashion. Then we thought that C would then rotate counterclockwise, so that'd be your negative direction. And then our sign convention was that delta was positive if it went to the right. Well, it turns out that we got a negative value, which is exactly what we would have expected. And eventually, it's not exactly, I guess. If you go back to the guessing video, we went through 3 different approaches before we finally settled that we thought that the frame would actually sway to the left, and that's what it turned out to do. Right, so now we've got those member end displacements. We can go back to the slope deflection equation and calculate then what the member end moments are. These, of course, are all in units of kilonewton meters, still using the positive sign convention that goes along with that equation. So let's translate those then into forces down on the member end. So MAB positive 17.6, that's clockwise at 17.6. At the top we have 27.6, again clockwise, which means that then for joint equilibrium MBC has to be the opposite direction, and sure enough it is. And at the far end then we have 25.3 clockwise there, and then turn that around over on the other one, and finally then 2.6 in a clockwise fashion at the bottom. Right, so that does enable us to do quite a lot in the moment diagram here, that we would end up with a moment diagram for the left hand column that would look something like this. That's a little out of scale. 17.6 at the bottom, 27.6 up at the top, and the beam becomes 27.6. It's going to be peaking at the point load. I don't know what that value is, and it's going to come down to about 25.3 here. So we need to go find out what that value is going to be. Let's get these other intermediate values in. That'll be on both ends. Ultimately a negative or frowny face on that. And then the left hand column is going to have a trapezoidal. Ooh, hey, that's just what we guessed. There's 2.6 there and 25.3 over there. Drawn on the compression side of the member such that we would have concavity that would look something like this for the deflected shape, which is consistent with exactly what we've shown up here as well. All right, so we need to go figure out what that is. That generally involves finding shears and those sorts of things. So let's come to this middle member. We got 25.3 at the right, 27.6 at the left. Looks to me like that probably means we have a shear like this. We've got the 80 kilonewtons on the member right there, and probably also a shear like this at the left end, and so that right hand shear, well, let's sum moments about, let's say the left hand shear, that is, let's sum moments about the right end. We get 27.6 plus 80, oops, yeah, right, sorry, 27.6 is the moment plus 80 times, this was a 2 meter distance, and then we got to get rid of the moment that's here, the 25.3, and divide by 5, and that's 32.546. Yes, if we want to be kind of close, that's a little bit more precision than we really have in any of the other numbers. And of course, if we subtract off the 80, we should get 47.54 here. Let's double check equilibrium and see if that works out right. All right, so 47.54 times 5 plus 27.6 minus 25.3 minus 80 times 3 equals 0, just like it should. So those shears are correct. Good. So that means then that the shear will come up 32.46, go over 3 meters, so 3 times 32.46, that's 97.38. Sorry, you can't see that. And then subtract off the 27.6 moment at the left end, that's 69.8. Then for that positive moment there, and then let's see if we get this to subtract off properly. Right, so that'd be minus 47.54 times 2, give us a negative moment of minus 25.3. That's exactly what we got. Looks like we did a good job here. And from there, of course, you could go find other internal force values. The shears in the column become axial forces, shear forces in the beam become axial forces in the column at 32.5, 32.5, and then down here, likewise, in here, you'd end up with 47.5 for the axial force in the right-hand column. So the right-hand column does get more of the load than the left. And then let's see, for the shears in the column, we've got moments that are trying to go clockwise, so those values will have to be going the opposite. 17.6 plus 27.6 equals, divided by 6, 7.5 or so. That becomes, of course, an axial force in the beam, and we hope that we would end up with then the correct shear value over here at the end of being 7.53. So let's see what happens. 7.53 times 3 meters be 22.6 plus the 2.6, and that's almost 25.2. So we have done pretty well there. Little rounding error only, and those are your final member and moments. These, of course, are giving you reactions: A over here at the left, D over here at the right.